Hello and welcome everyone. My name is David Steiner and I will be your speaker for today's webinar. I'm joining you on behalf of EnviroLogix, and over the next 45 to 60 minutes we are going to take a closer look at what's really happening inside a lateral flow device, and we will especially talk about why reference materials are so critical for getting reliable results. For those who haven't come across my work before, I am the head of the reference material division at LVA. LVA is Austria's largest private food testing laboratory. From my background, I am a food biotechnologist and analytical chemist, and I have spent well over a decade working on mycotoxin analysis and also on food safety, both in research but also in applied commercial settings. And what ties all of that together is a deep interest in the question, how do we know that our test result is actually telling us the truth? And that's precisely what we are going to explore today. So let's start with the central tension in this field. Lateral flow devices are, what we know, fast, affordable, and also require minimum training. So they are definitely the most widely deployed analytical tool in mycotoxin monitoring worldwide. But that simplicity also comes with a catch. It's all about balancing speed and also scientific rigor. And the workflow behind mycotoxin testing follows a clear logic, starting with representative sampling, followed by rapid LFD screening, where usually a decision point is reached, and where needed, confirmatory analysis is then conducted, for example, by LC-MS for regulatory grade quantification. LFDs are in this case not meant to replace confirmatory methods. They are the first line of defense, if you want. So they are rapid, high throughput, and deployed every day in grain elevators, mills, and also storage facilities around the globe. And precisely because so many decisions rest on these results, their reliability matters enormously, which also raises the question, if the test looks so simple, why do results so often vary? And in this iceberg graphic, I think it says it quite well. What you see is this fast, easy, portable test on the top of this mountain, which masks also a surprisingly complex analytical system underneath. So below the surface, you have matrix effects that can suppress or enhance your signal. We have cross-reactivity with structurally related compounds. We have extraction variability that determines how much toxin is even accessible, and also flow dynamics that govern how effectively the analyte is captured at the test line. And none of this is visible to the operator. The strip just gives you a line, and that line is the output of all these interacting variables. So it's clearly simple to use, but not a simple system. And the complexity is what drives the variability. So, and to understand this variability, we need to look at some data first. And this is actually where it gets counterintuitive. So whether you run the same sample 5 times, hand it to 5 different operators, or test across 5 different days, the variability looks essentially the same. So the CV around 20% in all 3 cases. There is no single condition which stands out as the major problem, which tells us something fundamental. So most variability doesn't come from the strip, and it doesn't come from the operator. It comes from the sample itself. So heterogeneous mycotoxin distribution is definitely the dominant source of uncertainty. And no test, however well designed, can actually compensate for that. And notice also where many of these data points land, right around the decision limit area. That's not a coincidence. That's the everyday reality of mycotoxin screening. And it's exactly why understanding what's happening inside the system matters, because that's where we find the tools to interpret these results also with confidence. So we have seen now the data. Now let's open the black box, because to really understand where the variability comes from, and more importantly, how to control it, we also need to understand what an LFD actually is as an analytical system. So when we walk through the mechanism, mycotoxin LFDs operate on a principle, for example, of a competitive immunoassay. So when the sample extract is applied, the target mycotoxin molecules encounter labeled antibodies that are already added on the conjugate pad. These antibodies can bind to the mycotoxin. As the mixture flows along the nitrocellulose membrane toward the test line, the antibody mycotoxin complexes then compete with immobilized antigen fixed at the test line. If there is a lot of free mycotoxin in the sample, the antibodies are already occupied and they cannot bind to the test line. So the signal there is weak or absent. If there is little or no mycotoxin, antibodies are free to bind at the test line, producing a strong signal. This means the signal is inversely proportional to the concentration, and it means that every step of the flow from sample application to line readout influences the final result. Now that we understand the mechanism, let's look at where variability enters the system, starting with the sample itself. So very important, mycotoxins don't distribute evenly through grain. They concentrate in specific kernels, what we call hotspots, as fungal contamination spreads through a lot. This means if you sample different locations within the same grain lot, you can get readings ranging from low to very high, even though it's technically the same lot. The practical implication is clear. No test, no matter how good the strip is, can compensate for a non-representative sample. A perfectly optimized strip with the best reference materials will fail if the sample doesn't really represent the lot. And this is why representative sampling is definitely the most critical step. Appropriate probe selection, multiple sampling increments, and also large composite sample, these are non-negotiable. And so that's where the story actually starts, with a sample that matters. And once you have your sample, extraction is your next control point. So extraction determines how much of the mycotoxin present in the grain actually ends up in solution on your strip. And this depends on multiple factors working together. So you have the solvent choice, the sample to solvent ratio, the mixing intensity and duration, and also the particle size. Methanol water mixtures are very common, but not all solvents are work equally well for every analyte matrix combination. Too little solvent reduces the yield. Inconsistent shaking introduces operator-to-operator variability, and particle size affects how accessible the analyte is. Incomplete extraction leads directly to underestimation. The sample looks cleaner than it really is. This is one of the most insidious sources of false negatives, and it happens before the strip is ever involved. On this slide, we can see the two main immunoassay formats. The top panel is the competitive immunoassay, so the format for small molecules like mycotoxins. Here, the signal is inversely related to the concentration. The more analyte means less signal at the test line, as already explained earlier. The bottom panel shows the so-called sandwich format for comparison, used for usually larger analytes like proteins. The signal increases with the concentration. So the key difference is very important. In mycotoxin LFDs, a faint or absent test line is positive. A strong test line means the sample is clean. This inverse relationship is essential for correct visual interpretation. Understanding this inverse relationship is also essential for correct result interpretation, particularly when reading strips visually. A faint or absent test line is a positive result. A strong test line means the sample is clean. So this is the key insight. Understanding variability is what unlocks better LFD interpretation. We have now covered sampling and extraction variability a little bit. Now we move into what actually happens inside the strip. And food matrices are actually very challenging for immunoassays. When you extract grain, you extract not just mycotoxins, you also extract everything which is covered in the matrix, including macronutrients like proteins, fats, oils, and carbohydrates, but also polyphenols, pigments, and salts. So all of these can, at the end, interfere with your analytical outcome and with your test. There are four main mechanisms. First, matrix components can physically alter antibody structure, reducing binding capacity. Second, non-specific binding. Compounds share structural features with your targets, occupying binding sites without being the analyte itself. Third, increased background signal from non-specific nitrocellulose binding, which can look like a positive result. And fourth, cross-reactivity between similar compounds. This is something we will address separately. The bottom of the slide contrasts ideal buffer conditions, a clean flow, specific binding, a clear signal. On the other side, with a real grain matrix, a real world matrix, we see an impaired flow, less specific binding, a weak or variable signal. This is why validating in a buffer, for example, alone would be insufficient. So real matrix performance is actually what matters. And the signal you see is not just simple chemistry, it's also physics. As the sample moves through the membrane, the analyte has a limited time window to bind to immobilized capture molecules at the test line. So this residence time is controlled by the so-called flow velocity. Slower flow means more time to bind and a stronger signal. Faster flow means the opposite. So what controls the flow rate? Matrix properties, for example, viscosity, ionic strength, particle size, and the presence of particulates or lipids. So two samples with identical mycotoxin concentration, but different matrix composition can produce meaningfully different signals. And this is a fundamental reason why matrix-matched reference materials are, at the end, so essential. Cross-reactivity, I've already mentioned that term, is another very subtle but also very important source of bias in LFD results. It actually arises from the fact that related mycotoxins, like the members of the aflatoxin family, for example, share common structural features, also known as epitopes, that are recognized by the same antibody. The four major aflatoxins includes aflatoxin B1, B2, G1, and G2, all share the same so-called difurofumaran backbone. So the antibody used in an aflatoxin LFD is typically developed against the aflatoxin B1, but because the other forms share key structural motifs, it will also bind to them as well with varying degrees of affinity. So now where do B and G series in aflatoxins actually differ? The key structural distinction lies actually in the right-hand ring system on this side. So the B series, aflatoxin B1 and B2, they carry a so-called cyclopentanone ring. This would be this. The G series have an additional oxygen atom incorporated into that ring, forming a 6-membered lactone ring instead. Within each series, there is a further distinction between the 1 and 2 variants. So aflatoxin B1 and G1, for example, contain an unsaturated terminal furan ring, this one here, meaning there is a double bond in that ring. This double bond is chemically very reactive and is also responsible for the notorious genotoxicity of these compounds. It is involved in epoxide formation and also DNA adduct binding. And importantly, this structural feature also contributes to stronger antibody recognition. The 2 variants, aflatoxin B2 and G2, they have a saturated furan ring without the double bond. They are less reactive, less toxic, and typically show lower cross-reactivity in immunoassays. However, the practical consequence is that the signal you measure does not reflect a single compound. It actually reflects the cumulative weighted contribution of all cross-reactive analytes present. So the test detects binding and not the identity. And because the cross-reactivity factors differ between analyte forms, the apparent concentration you read out depends on which forms are actually present and in what proportions they are present. So this is known as the matrix-dependent response ratio, and we will come back to it when we talk about reference materials. Talking about reference materials, this chain metaphor here is exactly right. You can have an excellent strip, a well-trained operator, and also state-of-the-art reader, but if you don't know whether the test system is performing correctly for your specific matrix and your specific application, every result you generate is only as reliable as the weakest link in the chain, and this weakest link could be the reference material you are using. And yeah, not all reference materials are actually equal. So the critical distinction is between spiked materials and also naturally contaminated ones. So the spiked materials are made by adding a pure analytical standard or a concentrated cultural material to a blank matrix. The toxin is freely available, not bound to matrix components, and also not modified by fungal metabolism. This makes it highly extractable, but it doesn't really behave like a real contaminated sample. Naturally contaminated materials, on the other hand, come from grain actually infected with mycotoxin producing fungi. The toxin exists in a complex state, so some are matrix bound, some converted to masked or modified forms alongside a full range of fungal co-contaminants and secondary metabolites. The consequence, spiked materials tend to overestimate LFD sensitivity. So you think your method is actually better than it is because you have been testing an idealized sample. For true performance assessment, naturally contaminated materials are therefore essential. So this framework actually integrates cross-reactivity and matrix effects. The key idea, the LFD signal does not reflect a single analyte concentration in many cases. It reflects a matrix-dependent response ratio, as we have already heard. So for aflatoxins, this ratio is relatively predictable. Aflatoxin B1 dominates with roughly a 10-to-1 contribution between aflatoxin B1 and B2. Compared to G1, the ratio is 10-to-3, for example. For fumonisins, the picture is similar. Fumonisin B1, 2, and 3 co-occur fairly consistently, but with a little bit more variability. For deoxynivalenol and I would say trichoticins in general, the situation is much more complex. So deoxynivalenol 3 and 15 acetyldeoxynivalenol and deoxynivalenol 3-glucoside can be present in highly variable ratios with significantly different cross-reactivity coefficients. The signal can swing dramatically depending on which forms predominate. So spiked materials distort these ratios by containing only one form at artificially high concentration. Only naturally contaminated matrix representative reference materials preserve the realistic analyte profile and also allow for correct interpretation. The particle size is also a fundamental determinant of whether a reference material is fit for purpose or not. If particles are too coarse, below 20 mesh, which is around 850 micrometer from size, mycotoxin contamination is not evenly distributed. So you get hotspots where some particles carry far more toxin than others. Small portions like 25 to 50 grams will have huge sampling error. Whether you scoop a heavily contaminated particle is essentially random. If particles are too fine, on the other hand, they tend to clump when especially aqueous solvents are added, altering extraction and also potentially clogging the membrane. So flow dynamics are disrupted and matrix effects could or can intensify. That's why the AOAC guidance points to approximately 20 mesh as the sweet spot, so to speak. It's fine enough for homogeneous distribution and coarse enough to maintain realistic extraction and flow. And this slide actually details the trade-off. So for LFD testing, optimal particle size balances good surface area for extraction, stable flow front, and also strong, consistent signal. Too coarse in this case means poor solvent penetration, reduced extraction, variable flow, and a weak signal. Too fine, on the other hand, this leads to aggregation upon solvent contact, altered extraction kinetics, slow and uneven flow, and again, a weak or variable signal. Interestingly, for LC-MS-MS, this actually benefits from very fine particles under controlled laboratory conditions where maximum extraction efficiency is possible, but that doesn't really translate to LFD use. So this creates a production challenge. The same material must actually perform well for LC-MS-MS and for the LFD. And getting that balance right is a key part of the production process of a proper real-world reference material. And with that background established, let me now introduce a specific reference material system we have developed at LVA, a novel quality control material designed specifically for both confirmatory testing like LC-MS-MS and also applicable for LFD testing. Particular emphasis was placed on ensuring the applicability across advanced analytical platforms, especially LC-MS-MS based methods. So the material was originally designed with confirmatory analysis in mind, as it also covers a broad and realistic contamination profile. In addition, the material was intentionally developed to evaluate its suitability for the lateral flow devices. So let me now walk you through how this material was actually produced, because the production process, as we heard, is integral to understanding its properties. So the starting point were 5 batches of naturally highly contaminated maize, so no spiked material. The contaminated lots covered different analyte groups, for example, aflatoxins and fumonisins in 2 batches, deoxynivalenol and seralenol, and also ochratoxin A. These were combined with, in total, 28 batches of blank maize or lower contaminated maize. The grain that had been tested and confirmed to contain no or low, very low detectable mycotoxins in this case. So all material was processed through an ultracentrifugal mill with a 0.25 millimeter ring sieve. So this actually achieves a critical particle size range, fine enough for homogeneity, but also preserving realistic matrix structure. The final blend, approximately 20 kilogram of the maize QCM, was pre-tested in duplicate by LC-MS. The target concentration was set close to the upper level of the relevant regulatory range, and the blending was then carried out over three production rounds to ensure homogeneous distribution without creating artificial hotspots. And this multi-round approach is important. Aggressive blending in a single pass can segregate particles by size or density, reintroducing heterogeneity. So 3 controlled rounds with intermediate testing could prevent this. To characterize the particle size of the final quality control material, we used the so-called laser diffraction method according to ISO 13320 standards. So for those less familiar with this method, a laser diffraction works by passing a laser beam through a dispersed particle suspension and measuring the angle and intensity of the scattered light. Larger particles scatter light at smaller angles, finer particles at wider angles. So from this scattering pattern, the instrument then calculates the distribution of equivalent spherical diameters across the entire sample, giving you a complete picture of the size range in one measurement rather than a simple pass or fail through a sieve. So the result is expressed as a cumulative distribution from which we read here 3 key percentile values, D10, 50, and 90. So these tell you the particle size below 10, 50, 90% of the material falls. And for our QCM, the D90 value is around 327 micrometer. This is a value that really matters here. So D90 defines the upper boundary of the bulk of the material. In other words, 90% of particles are finer than 327 micrometer. And that actually corresponds to a US mesh size of 50, which is around 300. So now think back to what we discussed earlier. US mesh of 20 was our upper threshold. Anything coarser then that risks heterogeneous analyte distribution and also hotspots. US mesh of 50 sits well below that threshold, so homogeneity is well assured. At the same time, the mesh size of 50 is still coarser than the ultra-fine powders used for LC-MS reference analytics, which typically go to a mesh size of 100 or beyond. And this means that our material sits right in this practical sweet spot, fine enough for confirmatory characterization, and yet not so fine that it alters extraction kinetics or flow behavior in the LFD. For a reference material to be used in practice, it also must be stable over time. So a lot-based QCM that degrades after 6 months is not viable for routine use. So that's why we've designed a comprehensive stability study covering in total 36 months. with measurement time points at 9 different time points. So 3 replicates of 30 gram each are prepared for each time point. Crucially, all time points are measured isochronically. That is, all samples are analyzed together at 12, 24, or 36-month marks. And this eliminates analytical batch-to-batch variability as a confounding factor. So you are comparing samples analyzed under identical conditions in the same run. 2 storage conditions are evaluated, plus 4 degree refrigerated and minus 20 degree frozen. So minus 20 degree condition here serves as the gold standard, preserving the reference material against any degradation for direct comparison. And the study design also follows best practices from ISO 17034 for certified reference material producers. The assigned values for the quality control material were established through an international laboratory comparison study. This is the process by which the target values are actually confirmed as scientifically robust. So in total, 13 laboratories contributed with 15 data sets. So each lab received 3 replicates of 30 gram, which with triplicate analysis by each lab, so generates in total 9 independent data points per analyte and per lab. The method mix is also quite notable. So we had 10 LC-MS data sets, 3 high-resolution MS data sets, 1 ELISA, and 1 HPLC DAD or FLD data set. 8 of these data sets were from ISO 17025 accredited laboratories, including, for example, national reference laboratories or official control labs. And 10 of these labs used stable isotope dilution assay, I would say the most metrological rigorous LC-MS approach at the moment. LFD testing was also conducted separately after the certified values had been established. So before we look at the LFD results, it's also worth briefly explaining how the assigned values are classified under the relevant normative frameworks. There is basically no single rule. So the classification really depends on the combination of how many laboratories contributed, which methods were used, and how many of these methods were used, what the uncertainty is, and also the level of metrological traceability achieved. The table here summarizes the general thresholds, I would say. So a certified value, for example, requires at least 8 different laboratories and at least 2 different methods. An expanded uncertainty should in this case be below 45% and fully traceable. An indicative value reflects fewer labs or also higher uncertainty, and an informative value is essentially exploratory, enough to give orientation, but not for regulatory claims. So this aflatoxin B1 data shown here is just one example from the characterization chosen to illustrate the quality of this interlaboratory agreement. So the data points cluster tightly around the certified values. As you can see, accredited and non-accredited laboratories perform comparably, and the statistical test confirms no significant difference between the 2 groups. So it's a very good agreement across all these 13 laboratories and 15 data sets from very different metrological backgrounds, and actually shows a very strong validation of the material's homogeneity. But the real significance of this characterization goes well beyond any single analyte. What this study also delivered is a full suite of assigned values covering not only all regulated mycotoxins, but also a broad range of emerging and unregulated compounds like, for example, monyliphamine, but also the acetylated versions of deoxynivalenol. A single naturally contaminated grain material carrying traceable assigned values across that breadth of analytes is definitely unprecedented. It's a milestone in the reference material landscape. So finally, the LFD testing was conducted by using standard field protocols, so 3 replicates per analyte, 2 operators, 2 separate days. The results are here expressed as CCE values reflecting the mycotoxin concentration seen by the immunoassay. So for the 2 most globally regulated analytes, including aflatoxins or aflatoxin B1, summarized as aflatoxins, and deoxynivalenol, the results are equivalent to the laboratory-based LC-MS methods conducted under these controlled conditions. Fumonisin and ochratoxin A show moderate agreement with the assigned values, and for zearalenone, the observed deviation reflects the analyte's structural properties. So zearalenone is a rather apolar compound with a predominantly aqueous extraction solvent. The particle size we choose doesn't allow us to hit the optimal extraction conditions for this substance. That actually is also reflected here by the result, but it's the right choice overall. It keeps the material suitable for both LFD testing and also for the reference methods. And as you could see, the agreement across all analytes is very good, which shows the material works very well across these different analytical approaches and also shows a very good applicability for LFDs. So we have covered now a lot of ground on the science. Now let's bring it back to the practical question. Given everything we know, we now know, what does fit for purpose LFD testing look like in real world? And everything points to one principle. An LFD doesn't work in isolation. It works within a system. And that system has actually 3 corners. The first corner, the reference materials. Naturally contaminated, correctly ground to the right particle size, representative of real world conditions, not a technical detail, it's the foundation. The second corner includes the standardized workflows. So you need clear SOPs for extraction, defined temperatures and timing, consistent readout protocols. This takes the complexity we have discussed and makes it manageable and reproducible across operators, different sites, and also time. So low measurement uncertainty comes from consistency in this case. And the third corner, the operator, often working in grain elevators or ports, not in a clean laboratory. That person needs confidence that when a result appears near a decision limit, the system behind it has been validated against realistic conditions and is performing as expected. Fit for purpose in this case doesn't mean perfect. It means designed to handle what it will encounter. And that's what gives LFD results value in real decision making. So, and this slide shows the 2 levels at which reference materials contributes. So together they cover, I would say, the full life cycle of an LFD from the development phase through the routine use. So during development and optimization, reference materials provide the defined reproducible test conditions needed to design the assay, evaluate sensitivity and specificity, ensure lot-to-lot consistency, and formally validate the method. Without them, each of these strips relies on ad hoc samples with unknown or uncertain properties. In routine quality control, The role shifts to ongoing performance monitoring. The workflow is straightforward. So alongside routine samples, a reference material is measured in each analytical batch. The result is plotted on a control chart in best case, as shown here, and checked against predefined acceptance criteria. Stable results within plus minus SD around the target indicate a system in control. A point outside plus minus 2 standard deviations, like the orange and red markers on this chart, triggers investigation before any sample results are reported. And this continuous monitoring is what turns a validated method into a trustworthy one over time. It provides documented evidence that the test system was performing as expected at the moment each routine result was generated, which is precisely what regulators and accreditation bodies are looking for. And one last question that comes up every day in grain testing, what do you do when a result is close to the regulatory limit? So the deoxynivalenol example here with an EU maximum limit of a little bit more than 1,000 microgram per kilogram shows something very important. Identical concentrations produce different signals depending on the matrix lot. That's analytical reality in field testing. Well above the limit or well below it, the decision is quite clear and the workflow proceeds accordingly. But in the uncertainty zone around the limit, between roughly 600 and 2000 microgram per kilogram, here the LFD is exactly what it was designed to be, a strong screening tool that identifies samples needing confirmatory analysis. That's not a weakness, that's the intended workflow. And this is where the matrix matched reference materials prove their value. They let you characterize your system's performance precisely in this critical range. When an uncertain result appears, you are not guessing, you already know how your system behaves in different matrices. You can explain the variability, and you can also make an informed, defensible decision about whether confirmatory testing is needed or not. And we are now already coming to the end of today's webinar, and let me now close it with 5 take-home messages. LFD performance is system dependent. So the result you get is not just a function of what's in the strip, it also reflects the combined effect of matrix composition, extraction conditions, operator technique, and also the test system standardization. Reference materials make LFD results interpretable. So without a material whose values are traceable and whose matrix mirrors real-world samples, you have no anchor for your results. Realistic materials are very critical. So spiked materials overestimate the performance. Naturally contaminated, particle size controlled, matrix representative materials provide the honest baseline you actually need. Reference materials enable confident decisions near limits. This is where the cost of uncertainty is the highest and where a well-characterized reference material provides its most important value. And finally, fit-for-purpose testing requires system thinking. No single component, not the strip, not the operator, not the reference material, operates in isolation. Reliable testing requires all 3 corners of the triangle to be addressed together. So thank you very much for your attention today. I hope this has given you a clearer picture of what's really happening behind the strip and why investing in the right reference materials is not a luxury, but a scientific necessity. So I'm now happy to take your questions. All right, I can see a few questions here. The first one is, what are the biggest risks when relying on spiked samples compared to naturally contaminated samples? So basically, as I tried to explain during the webinar session, the core risk is that spiked materials give you an overly optimistic picture of the performance. And that false confidence can have real consequences when you move to field application. So when you spike a blank matrix with a pure standard or with a cultural material, the toxin is freely dissolved and highly extractable. It hasn't aged into the matrix, if you want. It isn't bound to proteins or cell wall components, and also it exists as a single pure compound. In a naturally contaminated sample, the situation is fundamentally different. So the toxin may be partially matrix bound, it coexists with modified forms and co-contaminants, and all the full complexity of the food matrix is actually present. The consequence for LFD validation is significant in two ways, I would say. First, the sensitivity appears higher than it really is. So because spiked analyte is just easier to extract and detect. And second, and perhaps more critical for LFDs, is the cross-reactivity profile, which is in this case then distorted. So a spiked, for example, aflatoxin B1 only material tells you nothing about how the assay will respond to a naturally occurring mixture of the B1, 2, G1, and G2 cocktail in realistic proportions. So the matrix-dependent response ratio I explained to you is simply absent from a spiked material. So the practical risk is therefore 1 over validation, a method that looks excellent on the paper but underperforms in the field without anyone fully understanding why. Good. I have another question here. How does cross-reactivity influence decision making? Very important question. So cross-reactivity is, as I said in the webinar and in the last question, cross-reactivity is one of the most nuanced aspects of LFD interpretation, and it really influences decision making in ways that aren't always visible to the user. So as we discussed, particularly from aflatoxins and also the trichoticin family, detect a family of structurally related compounds simultaneously, the signal you read out is a weighted sum of all cross-reactive analytes present, so each contributing according to its individual cross-reactivity coefficient. So for aflatoxins, this is actually relatively well defined. As I said, aflatoxin B1 dominates, and the contributions of B2, G1, G2 follow a consistent pattern. The result can therefore be interpreted as a reliable indicator of the total aflatoxin burden, if you want. For deoxynivalenol and the trichoticins, the situation is a little bit more complex. So the acetylated versions of deoxynivalenol, 3 and 15 adstone, and also the glucoside conjugated form can be present in highly variable proportions depending on the commodity, also the harvest year, and the fungal strain. Their cross-reactivity coefficients differ from deoxynivalenol itself, which means the apparent concentration from the LFD can diverge meaningfully from the true deoxynivalenol concentration as measured by the, for example, LC-MS. The decision-making implication is this: when a result sits near the regulatory limit, cross-reactivity is one of the reasons why that result carries inherent uncertainty. So this is not a flaw, it is a known and quantifiable characteristics of the method. Using a naturally contaminated reference material rather than a pure standard is the most reliable way to understand how this cross-reactivity manifests in your specific matrix, and also to set acceptance criteria that are calibrated accordingly. So then we have another one here. How can reference materials be practically used in routine workflows to monitor and improve test performance over time? I think the practical integration of the reference materials into routine workflows is more straightforward than it might seem. And the return on that investment is definitely substantial. So the core principle is simple. Include the reference material measurement in every analytical batch. Run it under exactly the same conditions as your routine samples and record the results. So over time, these data points from a control chart, ideally in the format I have just presented, with the assigned value as the target and the defined acceptance limits, typically plus minus 2 standard deviations. That's the frame, I would say. This gives you at the end then 3 things. First, the real-time quality control. So any result outside this acceptance limits flags a potential problem before those routine samples results are reported. Second, a trend detection. So gradual drift, perhaps from a slowly degrading reagent or seasonal temperature effect, becomes visible before it causes an out-of-control event. And third, documentation, a complete traceable record that your test system was performing as expected at the same time each routine result was generated. For performance improvement specifically, I think the control chart over time is invaluable. So if you see systematic bias, consistently high or consistently low reference material results, that's a signal to investigate your extraction procedure, your solvent, or your operator technique. So if you see high variability without bias, the focus should shift to sample preparation and also to the homogenization. And ultimately, reference materials in routine use transform the LFD from, I would say, a tool you trust on faith into one you trust on evidence. So and that distinction matters enormously when results are used to make consequential decisions about food and feed testing. That's one last question here. Do temperature and moisture conditions influence LFD performance? Also very good question, and the short answer is yes. And this is one of the, I would say, more under appreciated sources of variability in the field testing, particularly when LFDs are deployed outside controlled laboratory environments. The temperature affects the assay at multiple levels. Antibody, antigen, binding kinetics are temperature dependent. At lower temperatures, reaction rates slow down, which can reduce signal intensity or extend the time needed for full development. At higher temperatures, the inverse can occur, so faster kinetics, but also potential destabilization of the antibody conjugate on the strip. So most LFD manufacturers specify an operating range, typically somewhere between 15 and 30 degrees, and results generated outside that range carry additional uncertainty. In a grain elevator, in winter or a warehouse in summer, those boundaries can easily be crossed without the operator being actually aware of it. And humidity primarily affects the nitrocellulose membrane and the conjugate pad. So high humidity can alter the flow rate of the sample through the membrane. As we discussed, flow rate directly determines the resident time at the test line and therefore also the signal intensity. It can also cause a pre-measure activation of the conjugate, reducing the amount of labeled antibody available to react with the sample. So the practical implication is quite straightforward. wherever possible, LFD testing should be performed under controlled or at minimum monitored conditions, and strips should be allowed to equilibrate to ambient temperature before use. Reference materials run under the same conditions as routine samples will naturally capture any temperature or humidity driven drift in the control chart, which is another reason why integrating them into every batch, not just occasional checks, is so valuable. All right, and with that, I think I'm at the end. I cannot see any further questions here in the chat. So let me thank you once again for joining us today. If you have further questions with respect to today's webinar or in general to products from EnviroLogix, please feel free to reach out to colleagues from EnviroLogix anytime. You can find the contact details here on this final slide, or just check out the website. It has been a pleasure. Thank you very much, and goodbye.